All right, so we're actually skipping a chapter. So we're skipping the ANOVA chapter, which is I think what 11 is. I don't remember. We're going from 10 to 12. So we're going to talk about two-way designs. So getting into more complex ANOVAs and dealing with interactions and post hocs on interactions. So glad he didn't try to come in just then. Would have had to tell him no. So Mitchell's taken to being weirder than normal, and he's like the stock man every class. I'm like standing right outside my classroom making faces at me. So I was like, tell me that's not Mitchell, but it wasn't. So anyway, we're going to do interactions today. Okay. So kind of getting started with what is a two-way ANOVA. And so anytime you see the word way, what they're talking about is the number of independent variables. So it's just a marker, a way to denote how many IVs you have. And honestly, that terminology is still in books, but I don't think it's going to stick in reporting research because it is not quite enough information. There are better ways to list these types of ANOVAs. But anytime you see a one-way, it's one independent variable, two ways, two, three ways, three. But when we add extra IVs, we're going to go back to talking about levels and conditions. So with between subjects ANOVA, so we're doing independent or between subjects ANOVA today, it's different participants in every condition. Okay, so independent meaning different participants. I wish we would call these independent ANOVAs because then it would make the t-test link a little clearer. So independent ANOVAs are independent t, but most people call these between subjects. Okay, and that's the way I learned it too. So sometimes people will call them two-way between subjects ANOVAs. So that indicates that all of the IVs are between. So everybody's in a different group. Sometimes two-way factorial. That is redundant because two-way means there's more than one variable. Factorial means there's more than one variable. So you're saying multiple variable ANOVA. And then just factorial ANOVA, which is really frustrating because that doesn't tell me really anything about the ANOVA except that it has more than one variable. So the way we're going to talk about them is on the next slide, but let me finish this first. So two-way repeated measures, those are evil. We're going to do this next week. So all of the independent variables are repeated. A two-way mixed, so one between, one repeated. And so those are the next two sections we're going to do. Instead of talking about them as two-way designs, though, we're going to report them in the more informative way. And what you'll see is this sort of style, 2 by 2 between subjects. Pick this up now. This is how Mitchell wants you to talk about them too. So another reason to really take this in. And what it is it's the number of levels for IV1, and then literally the X symbol by, is the way people say it, the number of levels for IV2. So if I say I have a 2 by 2 between subjects ANOVA, I have 2 levels for one variable, 2 levels for another. And that means there are 4 conditions, so 2 times 2. When I write these up in research projects, what I always say is 2 gender by 2 handedness, just to give you a goofy example. And so people know which variables which. If I say between subjects, everything's between. If I say mixed, maybe they're half and half. But just making it real clear how many levels and what variables there are. Much more informative. So now I know what to expect when I look at the ANOVA than just saying factorial. I don't know why this slide is fancy, but it is. So why do factorial designs? Why not just treat everything as one giant variable? But that's really because we want to understand interactions. So the point of this whole section is to get to interactions. So what interactions tell you is how much of the IVs, how much they really depend on each other. So I might be able to show that gender matters, but really it's gender and hand together that matter. Okay. That's usually more interesting than just the main effect. So looking at how those 2 variables work together as opposed to separate things. All right, if I'm looking at the assumptions, they're actually the same as a one-way ANOVA. So I still have to check for accuracy, mixing, and outliers. If I have missing data, I pretty much have to delete it because if they're missing something, they're usually missing the DV. And then you would be making up an entire participant. So that's no good. Don't do that. So we normally, with missing data, are just deleting people. There's still only one DV, so no additivity, so no correlations to look at. But it should be normal, remembering that the central limit theorem allows us to kind of treat that as robust if we have 30 people. Linear, and then we're going to use Levene's again, and almost good accuracy. So it's really the same, just this one doesn't matter. So. Next week we'll use additivity with repeated measures because we'll have multiple time points for each person. So back to levels and conditions. Each individual IV has levels. So the example we're doing today is about what's the word I'm looking for here? How happy people are with sports on campus. So we looked at gender, so we have 2 levels for that one. There are 3 sports. So we've got females and males. And then we looked at sport. So sports that they went to, none. And then I picked on football and volleyball. So we're just asking them to rate how satisfied they are with the sports, and we asked them which sports do you actually go to. So each one of those IVs has their own levels. So for gender, it's a 2 with 2 levels, girl and boy. For sport, it's 3, so it's a 2x3 ANOVA with which sport they attended. And so each one of these is conditions. So we have 6 conditions. It's really important that you get the distinction between levels and conditions now, because that affects the test that you're running. Okay. So levels out here, conditions in here. And the purpose of an interaction test is to look at the conditions. So I could just tell if I'm going to sports, do I have a different perception of my satisfaction with them? So if we're going to volleyball, hopefully we're very satisfied because our volleyball team is really awesome. I'm also partial. If we're going to football, this year we're doing better. Yeah. So, but if we're not going to any sports, I don't know what they're even judging. Right? So maybe I could just look at satisfaction overall. With sport, I could just look at satisfaction by gender. So maybe different genders have different satisfactions. But really I want to know if there's this interaction, or if girls who are going to the sports games have a different perception than maybe guys who are not going to games. Okay, so we're examining the inside boxes. We'll come back to across or down at the end. So this, I just wrote this out in box style. So we've got gender, sport, and satisfaction with athletics. That is what that's for. So I got ahead of myself, but this is how you would draw that up to create kind of the picture of the design for the experiment. And so we're going to kind of go back to talking about the underlying theory and a little bit of how the math gets back to that. And so this is from the book, talking about taking that total variability. So last week we had, here's the total variance that I could have, and we talked about this being cookies. And so I have all this variance, how I'm going to split it up. Last week we did model and residual, right? Or numerator and denominator. But now the problem is that I've got a lot more model going on. So this whole semester has been about what is our model. We've been talking about the mean is the model, standard error is a way to measure if our model's any good. So we still have the mean, but I could use the mean for none, ignoring gender. I could use the mean for females, ignoring sport. And I could use the mean for female none. So I've got 3 options. So that model gets broken into 3 smaller parts. You also often see this as A, B, and A by B. What they really mean is how much of it's due to just gender, how much of that is due to just sport, and then how much is left over for the interaction. So we're going to take model and break it into 3 pieces. Residual stays residual. It doesn't change pretty much. All between subjects residuals are the same. So this is that table from the F table explain thing that talks about how this works. A little less heavy on the individual math pieces in this one because it gets to be really long because there's a lot going on. But so sum of squares model, right, is still my mean minus the grand mean. So we had that humps picture last week where we said, here's the middle of the middle, where's each group in relation to the grand mean? But now it's conditions. So from last week it's levels, today it's conditions. So basically, how different am I from the overall average? And that tells me how much variance there is for each group. So we're taking conditions, my mean, minus the grand overall mean. Still the same concept as my group minus the middle. We're going to come back to each one of these. But that sum of squares model, I'm going to break into 3 pieces. Okay? The one for gender, the one for sport, and the one for both at the same time. So we're going to come back to this. So working through each one, we have to start with a total. So I need to know how much variance I have to work with, and that's the exact same as one-way ANOVAs. So each person minus the grand mean. That just tells me overall how much variance there is, ignoring all the variables, ignoring everything. Now our degrees of freedom is n minus 1. And so I have this feeling, like here's how much variance there is, given that nothing worked. Like all the experiments just, everybody's the same. So for this actually is for the example from the book, and I meant to take those out. But this is what the formula would look like. So I could take each person's score minus the grand mean, so sum of squares grand, times n minus 1. For sum of squares model, overall, we've got each group mean or condition minus the grand mean. And so that formula really ignores the fact that these conditions are structured. So it's still group mean minus grand mean. Like the concept is the same, but it ignores the fact that if I am female here, I can only be in one of these 3 boxes. I can't be in the other 3. So it ignores the structure of the data, which is never a good thing. So we're going to instead break it down by the structure of the data. So we're not going to pretend they're all the same IV as like 6 levels. Instead, we're going to force it to think about each IV separately and then together. And so this is what the formula looks like. Each individual condition minus the grand mean times the number of people in each condition. Right? So this is by conditions, not by levels. So let's say we're doing gender. I don't know why sometimes they like fly in. Sometimes they don't. They don't do that on my computer, but it'll keep you awake, I guess. So for gender by itself, it's going to ignore the fact that sport exists. So what we'll do, I don't know the means. We'll just make some up right now. Let's pretend this is like 65 and this is 55. These are called marginal means. So marginal means are ignoring everything else. So just girls, what do they rate? Just guys, what are they rating? And the nice thing, I think they're called marginal means. That's left over from the old days where you're calculating everything by hand and they're out in the margins of the table. That's what I think they're called. But if you ever see marginal means, all they mean is level means. And I would take each level mean minus the grand mean. So in this case, if the grand mean was 60, take 65 minus 60 squared, 55 minus 60 squared times the number of people at each level. And degrees of freedom is still tied to the number of scores that you're using. We're using 2 scores. Females, males. Okay, so it's k minus 1. Remembering k is levels. As opposed to n minus 1, back up here, because each person was part of this. Now just each level is part of this formula. Right. For sport, same idea. Our marginal means, let's say, if they don't go to sports, they think everything is great. If they go to football, they're like, oh, we're not Mizzou. And hopefully if they go to volleyball, well, what, Mizzou's not doing that hot this year either, so maybe we can all be sad in Missouri together. Right. But we're going to volleyball, we're really awesome. and they're really satisfied. Okay. Still marginal means again for sport this time. And now there are 3 variables involved. So non-football volleyball, so K minus 1 would be 2. So all we've done is we've taken that idea of group minus the grand mean and just altered which group it is. So for the first 2, it's levels minus the grand mean. And then for the last one, it's going to be conditions minus the grand mean. So these level means are considered marginal means because you'll see that term in your book. People use it off and on. That's sort of left over from the old days, I guess. Now the interaction is actually really mathematically pretty evil. And so all the books teach this as it's whatever's left over. So we're doling out the cookies and it gets whatever's left. So we control for the fact that this much of it's due to gender, this much of it's due to sport, everything else is what's left over. And this part changes depending on the type of ANOVA math you pick. And so that's one reason I think a lot of books are just kind of like, it's just the total. Because if I pick type 2 ANOVA, which is how the book tells you to do it with AOV, it depends on which variable I write first in my formula. So type 2 does it hierarchically. So controls for gender and then sport and then what's left over. Most researchers use type 3, which does everything at once. So gender given everything else, interaction given everything else. They do give you different answers. So we're going to do everything in type 3 because that's what SPSS does automatically. So if you're comparing your output, like your advisor ran it one way and you ran it the other way, you don't want different answers, right? Because that happened last year. And then it also controls for everything at once, which is a little bit more common of an interpretation. So the interaction is just whatever's left over. Or really, it's about how much my conditions differ from the grand mean. Error also doesn't change. So it's still average variance across groups. So each participant, you messed me up this morning. I blame you. Each participant minus condition mean. And then that's, remember, multiplied by n minus 1 for each group. So way down here. So the degrees of freedom thing, the way this works is it's in the number of scores that go into that formula. So when we're talking about models, it's the number of levels or the number of conditions. We're talking about error, it's the number of people. So back to this table. We've talked about total, mean minus my grand mean, that isn't changing. Residual, that's not changing either, but it's just mean minus my condition. So how different am I from my combination group? And really, this is where the new stuff is. So my level minus the grand mean, both of these. The interaction is just how much is left over, not due to levels. So our degrees of freedom, levels minus 1, levels minus 1. You would think this would be conditions minus 1. That would be too easy. Okay. It's levels minus 1 times levels minus 1. Okay. So it is these two multiplied together. And that's important when we get to power. So we're going to come back to that idea. Okay. Otherwise, it still divides going across. Okay. So sum of squares divided by degrees of freedom is mean square over here. And then each one of the models, so model 1, model 2 interaction, is compared to mean square residual. So all of them have the same error term on the bottom. So error is error until next week. And then each one has how much is due to the model to error. So that idea of the null hypothesis as good variance to bad variance, and the bad variance is the same for the whole experiment. Next week, that's not true, but this week it is. Okay. So repeated measures is kind of a monster. We'll talk about why they're monsters. But the concept is the same, but because if you're repeated, right, you're in multiple conditions, so I'm in all of these, I have to control for the fact that we've violated independence. Right, so between subjects, mathematically is a little easier to solve because each person is a different person. So I can partition the variance up really easy. So the cookies are easy to split. When we get to repeated measures, the cookies are all gooey together. I don't know. Cookie example doesn't work. But each person is repeated, so I have to control for the fact that they're in there multiple times. All right, so we're going to try running one of these. And thankfully, ezANOVA makes it easy. But this has come up, and it's actually on the homework for this week as well, so we're going to talk about it right now. It's like, let's say we have an order, there's an order to the experiment, especially if you're doing a trend analysis and you're trying to make the graph be in the right order. What if I want to change that order of levels? You can actually use the factor command, so command you already know, but no labels. So I'm going to refactor the column. Here's factor. And I just put the levels in the order I want. Remembering that those level names are in the data set. Okay, if it currently is like 1, 2, 3, you can convert them to 1, 2, 3, and then the words, and just reorder them then. So you could do, okay, no, I really want 1, 3, 2, and give them the right labels. But let's say you already have it labeled correctly, you can just reorder them here under levels. In this case, we don't have to have labels because they aren't changing. So let's actually try that first. So take a quick second to get the data set loaded up and to fix this gender problem if yours imports funny. Remember that it is call names, data set, square brackets. Be sure you capitalize gender or the code later won't run. And I'll give everybody a second to load that up. Okay, so let's just check the data set, see what it looks like. This is normally where you'd run all of your data screening. So we've got female and male, and I really want none to be first. So I really want to just move none to the beginning, because none in the middle seems a little weird. And then my satisfaction variable is from 0 to 100. Okay. So to move none to the front, I have my dataset name, sport, factor dataset sport, and I just have literally reordered them. So if we run that, okay, no labels, because the labels are fine, they look good. And then I run the summary again. Now you'll see they've just switched orders here, down here. So whatever order they come up in summary or table is the order they're going to come out on the graph and post hoc tests. So that's why we're working on reordering them. All right. Since we're still doing between subjects, we want to get Levene's. But the nice thing is that ezANOVA does Levene's for us. Ooh. So we're going to first add ourselves a participant number. But this is just a reminder of what ezANOVA looks like with the caveat that this thing is new here. So we've got data as the dataset name, so everything on the left stays, everything on the right changes. DB is the DB column. Between here, you would think you could use a C or the word list. No. Okay. So I'm not sure why they didn't write that way, but it's a dot. Okay. So it's dot parentheses. If you leave out the dot, it will throw an error at you. If you just try to put commas there, it also freaks out. So dot parentheses. And it gives you both, you put in both IB columns. And then this is staying the same. So participant number type equals 3. So we all get the same math. And detailed equals true. All right, so let me install ezANOVA because I forgot. Typing is hard. Okay. Nope, still thinking. So, something fun. I was, one second, talking to a friend of mine about some other package, and he was trying to run some code for me, and he was like, well, not found. I'm like, did you load the library? And he looked at me, he was like, did you just teach on me? I was like, sorry, I said that a lot this week. Yeah, Adam?
Mine says they can't find. Is it easy?
Yeah. You on your computer or school computer?
Oh, this computer.
Yeah, you'll have to install easy.
I put install.packages.
Mm-hmm. Open parentheses. It has to be in quotes. Yeah, install quotes, library no quotes. Wildly inconsistent. Did that work?
Install no quotes?
No. Well, here, just click packages. Click install. Easy. Okay, so I'm going to make sure I load the library first. Okay. So 19 here, we're going to run to add ourselves a participant number because we have to have a participant number for easy to work. And then all we've really done from last week is seriously just add two variables here. Okay. That's going to give us a very different output, but we're just kind of tacking that little bit on. All right. So I'm going to check that out. Should get this craziness. I turned off scientific notation so that P was a little easier to read. And then if you're still trying to get yours to work, I have the output here for Levene's. Okay. So I've got to run the ANOVA to look at it. But first thing I want to check is Levene. So we're still kind of in data screening mode. Levene's treats the analysis of variance on variances as one giant level. So it doesn't control for like the conditions. It just takes everything as one giant group and tests all the conditions against each other. So that's where the 5 is coming from. Got 6 conditions, testing them all against each other, and then it calculates a ANOVA on the variances. That's normal because if you have differences in conditions, you've got a problem. Okay. It's not significant. So here's 5 and 42. So degrees of freedom, model and residual, or numerator and denominator. Here's F. We're looking for 0, 0, 0 would be bad. So less than 001 would be bad. And it's fine. So we don't have to do anything fancy, which is good, because the way to fix these when they're messed up is harder than the one-way dot test. When we get to the actual ANOVA here, we're going to ignore the intercept. So ignore that line. And now I've got 3 F tests. Okay. So if you have a two-way ANOVA, you're going to get level 1, level 2, and the interaction. And the little dots here just mean the interaction. So we've got 1 for gender, 1 for sport, 1 for the conditions. And I'm going to kind of walk through each one separately here in a second. But what do I do now that I have these 3 effects? So still have GES out here for generalized effect size, which is a form of eta. But I have 3 of them. So what does that mean? And instead of doling them out, so taking all of the effect and saying you get this much effect, you get this much effect, we actually are going to do what's called partial eta. It's for each test separately. You can also do partial omega, so we're going to try both. And what that does is it says, okay, given this test all by itself, how much does this test matter? Okay. So instead of being estimated on a total amount of variance, it's actually only estimated on error. Okay. So regular eta, this is regular eta. Ooh. Wait, just kidding, this is partial, sorry. Regular eta is sum of squares model over sum of squares total. But as you will notice, in our output here, we still don't get total. Now we could calculate that by adding up gender, sport, gender by sport, so these 3 and the denominator. But that's too much work. So instead, we're going to do partial eta, which is sum of squares model, so same numerator, sum of squares error and model. That is not total. Okay. So these 2 models are the same. So sum of squares sport over error plus sport. But that ignores gender and the interaction. That's what I'm saying. Okay. So total is normally gender, sport, and gender by sport. And we've just dropped those 2. So partial ADA only looks at the individual omnibus test. It ignores the fact that there are other tests going on. If I only have one IV, partial and total are the same, which is why we didn't talk about partial last week, because they're mathematically equivalent. But with multiple IVs, they're not. And what that means, do I have this? No, back up here, is that sometimes it adds up to over 1. And sometimes you get a reviewer that doesn't understand math and tells you that you've done something wrong because they can't add up to over 1. And I'm like, actually, mathematically they can. We had to write a proof for this poor person. But they don't hear, but they can add up to over 1 because they have different denominators. Generally, when we're dealing with people, we'll get small effects because remember, 0.15, 14 is a large effect. This is made up data, so sometimes when you make it up, it's really easy to make them up where they're really large effects. So generally, you'll see lots of little effects. Now, omega is actually a little easier than last week. Woohoo! Right? So it's A minus 1. Okay? So A here is the number of levels. I didn't get to make this up, so it should be K if we're talking about using the terminology people use now, but if you look at the book, this is cut and paste from the book. Okay. So it's A minus 1. So it's degrees of freedom. So degrees of freedom model. So for gender, that's 2 minus 1 times the F statistic for it, minus 1. Divided by the whole thing, plus, and this is the hard part, levels times N. So we're going to talk about how do I look up N and make sure I'm using the right N. So it's the number of people in each level. If I'm doing gender, if I'm doing the interaction, it's the number of people in each condition. All right. So let's try all that. So looking at the output, come up here. Just for gender. So it's in order. 1 and 42, so that's 2 minus 1, and then 24 minus 1 plus 24 minus 1. Blah, 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 F. Okay, so 2.03, which is not significant, so here's P. The bad thing about turning off scientific notation is sometimes you get this mess. So it's not significant, and it has a small to medium effect size. So 0.05 is kind of mostly towards medium, but still in the small category.
I don't understand when you said 24 minus 1 plus 24 minus 1.
Wait, that would add up to 26, wouldn't it?
46.
46, you're correct. So I must not have how many people are in each group right in my head. Hold that thought. 2 levels, male and female. Right? Oh no, I'm sorry. Degrees of freedom error. I just said that wrong. You were correct.
Okay.
Here. Is still N minus 1 plus N minus 1. So it's actually 8 people. 7, 7, 7, 7, 7, 7. Yeah. I said last week's code. Right. So it's N minus 1, but still by condition, not by level. Thank you. Good catch. Now I forgot where I was. Medium effect size. Okay, so it's somewhere between small and medium. Sport here, 2 and 42, so same one for each one, is 20. So that's going to be significant. So our p-value is less than 0.001. It's a really big effect. So 0.15 is large. Right from your notes last week, so 49 is really large. And then because I made up this data, gender by sport is also significant, and it is also a large effect. So we have an interaction. You would not do these types of ANOVAs if you didn't want the interaction. I think it would be pretty rare for you to have variables that you didn't want to interact. Otherwise, why are you studying them together? Like, why are they in the same experiment? Unless you're trying to talk about order. So in some people's studies, they also include the order that the conditions went in, and they don't want that to be significant because that would be usually a bad thing. So they're hoping it's not, so they can drop it out. But generally, if you have a variable in there, why are you doing them together if you don't care about how they interact with each other? So to write these up, we would do dfn, dfd, or residual f, here's p, and then in p2. So you gotta add that little p down there for partial. If they were overall ADAs, they would all be the same for each one. Okay. Or they would actually be slightly different for each one, but they would all have the same denominator. And so they should add up to 1, or they add up to something less than 1. So making sure that you just put the little p in there so the reviewers don't get confused on which one you're doing. All right, so we're going to graph just the main effects just to see what happened here. Generally, you don't do that, but we're just going to practice. And then graph the interaction, and this is the one you generally put in a report. So to do those, I have not installed ggplot. Oh, I think it installed with me. Oh, too late now. Stack Overflow. Did anyone get this? Anyone click on this? Stack Overflow is a great place to get help. Nobody? Oh, pity. That's fun. About once a week, I'm like, thank God for Stack Overflow. Because they answer my questions. All right, so we had run this ANOVA. It took off easy ANOVA for me for fun there. So from this ANOVA, now let's talk about omega, and then we'll make our graphs. So how do I calculate the right n for my omegas? And that's where the table function is really useful. Okay. So I'm going to calculate a table for each one. And so for my gender omega, which I did as an O this week instead of W, is 24 in each group. Okay. So n out here is 24. For my sport variable, it's 16 for each group. So n at the very end here is 16. But to get a table for the other one, you can actually do the table function on 2 variables. Do gender, comma, dataset, $, sport. Right, you can do that, or you can use tapply and do length. And this is something we've done a couple of times now. We've talked about calculating standard error, calculating the means. So either one would work. So both functions work. Don't ever try to do table on a complete data frame. You will crash R. Because it's trying to give you every possible combination of every variable. I have done this many a time stupidly. Okay. So the table function, if you're going to use 2 variables, be sure you tell it just the 2 variables and not the whole data frame. Because you would think what that would do is just give you a table for each column. That's not what it does. Okay. This is very similar to crosstabs in SPSS. All right, so then I would just fill this in. So degrees of freedom are first. So I got 1, 2, 1, 2. F for each one, and then n. So I think n's the hardest part. So that's where I got my 24, 16, and 8. 2, 3, and 6. Where do those come from? Okay. That's what A is. So 2, gender has 2 levels, girls and boys. 3, sport, 1, 2, 3. 6 is the number of conditions. So 2 times 3. Leave in all of the parentheses, or you will math incorrectly. All right, questions on where I got numbers from, because I know last week that was like, wait, where did this number come from? So it's a little easier because you don't have to figure out mean square residual. Right? The hardest part is making sure you get A and N right. So let's see what those are. So with the ezANOVA, we found for partial eta, we have 0.05, 0.49, 0.36. I got 0.02, 0.44, 0.31. Remember, they should be smaller. And it is. If you get an omega that's larger, you've done something wrong. It will always be smaller.
For the gender and the interaction one, is there a reason like the last little times one isn't in parentheses, but sport is? Like the 6 times 8, 3 times 16, 2 times 24?
Oh, no.
Does it make a difference?
Not mathematically, no. I mean, you could put them there.
They're just confusing that I have one list of what you have to work.
Well, actually, I only did it on the middle one. No, but the minuses need those parentheses, so they get minused before they multiply. The multiplication parts, no. The main concern is here, right? So this minus has to happen before I multiply it in each one of those f-1 cases. So not incorrect, but if you want to add them so they all look the same, you can. Yeah, so I got the same answers. All right. So where are we going? We're going to do pictures, then we're going to take a break. So if I do a level picture, so if I ask you create me a level picture, it's a one variable bar graph. So I copied all that code from chapter 4. Just made myself a one variable bar graph. And my HMISC is not working, so it doesn't create it, but here's what it should look like. Now I could make this go from 0 to 100 because that's the scale we're using, so that I don't distort the differences between groups. But really want to make sure that we have all of our labels properly capitalized, it has error bars, that sort of thing.
Can you tell me how to do that? How to make that go from 0 to 100?
Yeah. So what you want to do is add a plus at the end. The code is chord with 2 O's underscore Cartesian. So chord Cartesian. There's a couple ways to do this, but this is the easiest one. So ylim, because we want to control the y limit, equals C lower to upper. Oops. So I want it to start at 0 and go to 100. You can also do that with x, but right now, since x is categorical, it will have a fit if you do x. So that should switch to the top.
That makes me so happy.
I think that's on, it talks about it on the, no, the homework, yeah. Okay, now if I run this again with HMISC installed, I should get the little bars. But if I look at this graph, I see that they're not different. But if I zoom out and use the entire scale of the data, I can really tell they're not different. So guys and girls are marking these as the same. So our overall averages are roughly equal. Okay? And they're not statistically different. And I can also kind of tell that there's a lot more variance in the males and in the females. If I just wanted to look at sport, and now that we've reordered them, they make sense. Okay. So if you go to no sports, you're like, yeah, sure, great, whatever. If you go into football, you're unhappy, right? And if you go into volleyball, you're like, yay, wonderful. So the difference here is probably that football is less than these two. But since there's 3 of them, I can't do anything yet. I can look at it and go, well, it's probably less, but I don't have the post hoc test yet. And then if we want to make the interaction graph, so I added, this is a new little piece, scale fill gray. What we talked about before was scale X discrete or scale X manual. We could change the colors of each set of bars. Another option might be scale fill gray, which fills them in gray. So just a little tweak thing that you can learn. I still think it's hard to read the error bars on these graphs, but it is an option.
Do you have to do it gray, or can you put it different?
You can generally put them in color. It depends on the journal. So some journals charge you to print in color online.
I just meant, can you actually you said scale fill like blue.
I don't know.
Red doesn't work.
Red does not work apparently. Blue doesn't work? Let's try white. I knew gray was a thing. No, it doesn't like that. And I think you can spell gray either way. I'm fairly sure. It has all of the British spellings for the word color in here too. No, you can't. I lied to you. It has to be E. I've always spelled it with an A, but anyway. Okay, there's my interaction bar graph. And what I can see is that guys are really unhappy with the fact that our football team, especially when I made this graph, was not doing so well. And the interaction is because there are these different patterns of data. And that is a good place to pause and take a mental break. Because then we're going to talk about what does an interaction mean.